of the NPTEL course Fundamentals of Theoretical and Experimental Aerodynamics, being held on the 17th of April 2025. I am Professor Arnab Roy from Department of Aerospace Engineering, IIT Kharagpur, offering you this course. Let me once again introduce the course details. Uh, as you can see, this is a rerun course. We are running it once again during January to April of 2025. The final exams are coming very soon. I'm very ably supported by my course TA students, Mr. Arpit Mishra and Mr. Arjun Garva, research scholars of Cryogenic Engineering Center, IIT Kharagpur. And our team is very ably supported by a very large number of NPTEL technicians, staff, and professors, both at NPTEL office IIT Kharagpur as well as NPTEL IIT Madras. We are extremely indebted to our entire team for making all this happen. And last but not the least, and most importantly, the participants of the course make it successful. So we are extremely thankful to the participants for having enrolled for this course and making this course happen once again as a rerun course. We are very happy to interact with you from time to time through different media, including the live sessions that we are running, as well as the interactions through the Google forum. We are very happy to see that a lot of interaction is actually happening between us, the team offering the course, and the recipients of the course. And we are delighted to find participants spanning from academia to research organizations, industry, defense forces, and very active participation from all of them. With that, let me move on. And we found one very important question from the Google group for this live session. Let us discuss about this question, and then we'll have a quick recap about the course contents. Those who are going to write the final examination for the course, I think you must be preparing very hard to perform well in the upcoming examination. So a quick recap through the different weeks, materials may be useful, and I'm sure that you must be solving the assignments at this point, also trying to work out some of the relations which have been derived, some of the concepts which have been taught all through the course to small derivations. You should be practicing all this, also solving some numerical problems and some conceptual questions which depend on things that you have learned all through the course. Let's look at this question. It is related to assignment 8, question 12. The question is, what is the approximation of the governing equation of Stokes' first problem in backward time central space, which we abbreviate as BTCS, if kinematic viscosity is given by the value that we have here and the spatial grid size is delta y equal to 0.001 meter and the time step is 0.01 second. And as always, you have 4 options. You have to choose the correct option, or sometimes for certain questions, it may be multiple options. Incidentally, for this question, the option D is the correct one. But because we have one of our participants asking for further explanation or some more discussion about this question, before we actually look at what the final answer is, we should look back at the concepts which are important related to this question. The first thing that we realize is that the question is related to a parabolic partial differential equation. And from the point of view of the solution of a parabolic partial differential equation, when we solve it in the XT space, we remember having seen this figure earlier in the course where we try to draw the domain in the XT space, where the spatial domain spans from x equal to 0 to x equal to L, and the time starts from t equal to 0 and it extends up to infinity or some finite time that is defined by the need of the solution. If you look at the characteristics-based solution of this kind of a problem, you remember that parabolic partial differential equations have one real characteristic. So the information propagation happens the way that we have indicated using those small black arrows over here. So at a point Pxt at which the solution of the governing, this should be parabolic equation, I'm sorry, is being studied, the information will propagate from all directions the way it is shown in those, using those black arrows. So the entire region below it happens to be the domain of dependence. And if you recall that this is actually a marching kind of a problem, it can apply to transient heat transfer, unsteady flows, and marching problems can also lead to wave propagation kind of problems, but those problems are dealt with using hyperbolic partial differential equations. The flow direction acts as a time-like coordinate along which marching is possible. And coming to the parabolic partial differential equations, they describe time-dependent problems which involve significant amount of diffusion. So the examples are unsteady viscous flow and unsteady heat conduction. Now, the Stokes' first problem is related to unsteady viscous flow kind of a problem. If you look at the mathematical nature of the problem, it is an initial boundary value problem, because you remember that in the xt space, whatever you define at t equal to 0, from x equal to 0 to x equal to L, that is basically your initial condition, because that is what you are specifying at t equal to 0. And then at t greater than 0, the solution is bounded by the boundary condition, which is applied at x equal to 0 and x equal to L. So whatever way the function varies within that domain x equal to 0 to x equal to L, it must be bounded by the boundary values. At disturbance at a point in the interior or the boundary of the solution region can only influence events at later times, and the solutions move forward in time and diffuse in space. So the diffusion basically happens across the spatial expanse of the domain. The occurrence of diffusive effects ensure that the solutions are always smooth in the interior part of the domain at t greater than 0, even if initial conditions contain discontinuity. So they will tend to get diffused out as time elapses. The steady state is reached after a long time, and the equation then displays elliptic kind of behavior. We can show that at long time, the time dependence in the solution goes. So we are basically left with a second order spatial derivative on the right hand side, and it takes up a form similar to the Laplace equation, and therefore it behaves like an elliptic equation. To go more into the details of the problem, in Stokes' problem, this is how the whole thing looks like. You have two infinite parallel plates, which are shown in this figure, and there is a viscous fluid filling the gap, and it's a Newtonian fluid also further. And you keep one of the walls stationary all the time, but you give some motion to the other wall instantaneously or impulsively beyond t equal to 0. And then onwards, the moving wall continues to retain that velocity at all t greater than 0. So the motion of a viscous fluid inside the straight 2D channel induced by sudden acceleration of one of the walls of the channel is what comprises the Stokes' first problem, and the governing equation is basically given by this. So the u is a function of both t and y being this direction. So you can measure the y from the lower wall where y could be equal to 0. And kinematic viscosity or momentum diffusivity, depending on you know, this values of nu, is a fluid property which enables the fluid to transport momentum in the presence of appropriate velocity gradient. So it must be accompanied by velocity gradient, only then it is effective in terms of diffusion of momentum. And then you have already learned through the discretization approach how to tackle this kind of a partial differential equation by using different kind of schemes which work. Basically, we use the Taylor series expansion to replace the derivatives with different orders of accuracy. So you may recall about an explicit scheme which is called as the forward time central space discretization, which we have learnt about. And in that, the the time derivative that we have on the left hand side of the equation is discretized in a form like this: ui n plus 1 minus ui n by delta t, which is actually a first order accurate representation of the time derivative. And the second order derivative in space is discretized with a central difference scheme. And you can remember that the stencil, if you were to look at the stencil this way, where y is this direction, and it's basically marching in time. So it's basically saying that this is the time axis. And in discretized sense, you have different time levels. So this is the nth time level, this is the n plus 1th time level, and so on. So at every time level, you have all the grid points which have discretized the y domain dimension. And the same discretization repeats at different time levels, forming this mesh. And because it is an explicit algorithm, all the right-hand side terms which are shown over here are from the nth time step. If you look at ui plus 1 n, then it is this point. Then ui n is basically this point, and ui minus 1 n is basically this point, where I is the index used for discretization along the y direction, and n is the index used for the time level, and the spatial grid is denoted through the subscript, and the temporal step is denoted through the superscript. And you see that all terms on the right-hand side belong to the nth time step, while one term on the left-hand side is dependent on the nth time step, while the other is dependent on the n plus 1th time step. So in this entire algebraic equation, there is only one unknown. And therefore, the information basically propagates the way these arrows indicate over here, that you have information propagating from these three grid points, which are at I minus 1, I and I plus 1 respectively at nth time level, influencing the solution at n plus 1. Now, this is what we call as the forward time central space discretization. So we are actually moving this information available at nth time step in a kind of a forward direction in terms of time, and by centrally differencing the spatial derivative, second order derivative, when we do this discretization. Now, since it's an explicit scheme, it is what we call as conditionally stable, and therefore you cannot use any kind of delta t that you would love to use. Sometimes if you use too large a value of delta t, then the solution will become unstable. This can be proved through what we call as the von Neumann stability analysis. And as you march the solution in time, you will be able to see the variation of u through this gap. At some intermediate time, the variation may be looking like this. At large times, it may be looking like this, where you already have a linear variation of velocity starting from u equal to 0 to u equal to, say, u infinity, which is there on the upper plate. So this is basically how we deal with parabolic PDs when we do it in explicit manner. Now, coming to this next slide, where we have just turned around the domain, and instead of vertical, we have made them horizontal, just to accommodate two different discretization schemes which we want to discuss. With respect to the doubt that has been raised by the participant, we are more interested in this scheme, though I have retained the forward time central space discretization we discussed in the previous slide, once again in this slide on the left side, on the left part of the slide. And if you remember, we said that it's an explicit scheme as far as this FTCS is concerned, and it is conditionally stable. Now, looking at backward time central space discretization, why we say backward time is because here in this scheme, we do not look at the solution at n plus 1th time step by moving all information forward from the nth time level. Rather, there is only one point which is lying at the nth time level from which information is propagating out. And therefore, as far as the solution for these three grid points are concerned, we have to look back in time to the nth time step level. That means you are seeking the solution at 3 points at a time at the n plus 1th level, and which basically means that it cannot be obtained in an explicit manner. So that is how this scheme actually is an implicit one. And by using the von Neumann stability analysis, we can formally prove that it actually gives us unconditionally stable scheme, which means you do not have a restriction per se on what kind of delta t you would like to use. You are free to use any value for that matter, though if you use very large values, then the solution accuracy will get compromised. However, the steady state solution may still remain uncompromised, which you achieve at large times. However, the intermediate time step solutions will become inaccurate if you use very large times, but nevertheless, it will remain stable. So it inevitably shows you the difference through the kind of stencil that we have. So here we are invoking information from three different spatial grid points at nth time level to generate information at one grid point at n plus 1th level. And here we are trying to generate all these values simultaneously by invoking information from one point. And that one point information has to be sought by looking back in time. And that's how the name backward comes up in this discretization name. Now, to implement this, how do we go about it? So when we do the time stepping, we write it as ui n plus 1 minus ui n by delta t, which looks exactly the same as what it is over here, but the interpretation now becomes different. Instead of forward what we said over here, the same discretization here has a different context. It's actually backward because you are talking about simultaneous solution at the n plus 1th level at multiple points, for which you step back and you get the solution at the nth time step here. And as I said earlier, that we are looking for simultaneous solution at multiple points. Therefore, the second order spatial derivative here, which is centrally discretized, is being obtained at the n plus 1th time level instead of n. If it was n, then it would have been an explicit discretization. Now, having said that, this equation cannot be solved on its own. It has to be solved simultaneously with other equations which are actually going to come up from neighboring points. Here, this solution is centered about this point. So there must be an equation centered about this point. There must be an equation centered about this point. And these values are not unknowns. They are going to come from the boundaries. And therefore, finally, you will have a set of three equations to solve for these three unknowns. So that's how the solution has to be obtained in this case. Excuse me. If you rearrange these terms, you will see that ui plus 1, n plus 1 will have a certain coefficient like this. Ui n plus 1 will have another coefficient. Ui minus 1, n plus 1 will have another coefficient. All these three are unknowns. The only known term is ui n, which you obtain by backward stepping. As I said, this is a linear equation in these three variables. You have to write down similar linear equations for the neighboring points, this one and this one. Though when you write this linear equation for this, you will see that the number of unknowns will be reduced to 2. Why? Because this will no longer be an unknown. It will come from the boundary condition, while this and this will be unknown. While when you write this discretized equation for a grid point like this, centered about this grid point, this will be an unknown, this will be an unknown, but this will be a known. And therefore, there will be two unknowns in that equation, which means only for this reference point, there is a linear equation in three variables, while the equation for centered about this point has two variables, the equation centered about this point has two variables, and finally, you therefore have three equations to solve, which should help you solve these three variables simultaneously. Therefore, the solution altogether moves to the next time level n plus 1 when we solve these three equations. A very efficient algorithm is used for solving such a system of linear equations. That is what is called as the tridiagonal matrix algorithm. We briefly say TDMA. So having discussed about this background, now you can revisit that question, and I'm sure you should be able to work it out yourself if you try. And remember that this is the governing equation we are talking about. It would be very similar if you were talking about time-dependent heat conduction equation, in which case the variable, even if I call it as U, would actually have the interpretation of temperature. And this Y could as well be X or Z or some other direction, as long as it is in the Cartesian space. And then you use backward time central space discretization to give this form, and then just plug in the values which are stated in the problem. So you have to obtain this value, and it's obtained as this. So that is just plugged in over here. You rearrange the terms in the equation, it comes out like this. So that is one of the options which is given in your answer set, and thereby you can get the correct options. Correct option, sorry. So that's a brief discussion about that problem. And then, as I said, that we are very quickly going to recap the contents of the course, spending just 1 or 2 minutes on each one of the week's contents. Just to recap that in the earlier part of the course, in the first 6 weeks or so, we had discussed about the theoretical aspects of aerodynamics, and then we had a very brief introduction to the computational aspects, perhaps in the 7th and 8th week, and then 9 to 12, the last 4 weeks we spent on discussing about experimental techniques and facilities and things like that. So that more or less gave us a kind of overview of theoretical and experimental aerodynamics with a little bit of computational aspects also. So the week 1 introduced the basics. It also gives you the appreciation about the major components of aerodynamic studies, the theoretical approach, which includes analytical or semi-analytical solutions of governing equations. Then in between, we discussed about the numerical computations or CFD, and then finally we discussed about experiments and the appreciation that they all complement each other, they validate each other, and a modern aerodynamicist should have a very good balanced perspective of all these approaches so that she or he can do a good job. And then we introduced the concept of standard atmosphere, where you learned about geometric absolute and geopotential altitude. We talked about the temperature distribution, isothermal and gradient regions within the atmosphere, the equation of state, how it is to be used for obtaining the pressure and density variation through the atmosphere, and remembering all through that the compressible nature of air essentially shows up through these variations. Important concepts related to aerodynamic flows, pressure density, temperature, flow velocity, skin friction, these were discussed. And then we discussed a little bit about the genesis of weight, lift, thrust, and drag forces acting on the aircraft, how the flow has to turn in order to generate lift, how the thrust equation works out for an air-breathing engine. And if you learn that, you should also be able to write it for a rocket engine, for example. Drag forces, where do they arise from? So there are different sources like skin friction drag, pressure drag, induced drag, form drag, wave drag. And we also appreciate that all these four forces should balance each other in terms of pairs. So weight balances lift, thrust balances drag if the aircraft is in steady level flight. And then we learned about integration of pressure and shear stresses to obtain forces and moments on an airfoil. the relation between normal force, axial force, lift and drag forces as a function of angle of attack. We learned about the significance of non-dimensional coefficients, and we learned about a few which are very important, like pressure, skin friction, force, moment coefficients, how the nomenclatures work for a 2D body and a 3D body, the different uh, control surfaces on an aircraft which can be deflected to generate different forces and moments. We have three forces, three moments acting in general on a 3D body like that. So, so we learned about the Euler-Nernst control volume approach, and we learned about Lagrangian fluid trajectories like streamlines, path lines, and streak lines. We learned about fluid kinematics, things like angular velocity, curl of the velocity vector, vorticity, strain of a fluid element, rotational and irrotational flow, circulation, vorticity, velocity, potential. Some of the very, very important fundamental concepts in dealing with fluid kinematics. I'm sure you all must be remembering the definition of all these um, terms, and you should be able to make small sketches to explain the concepts or write down equations to explain the concepts. Please try doing it on your own to self-test your learning. Then we also did a brief revision of mathematical concepts related to vector calculus, most often the gradient divergence, line and surface and volume integrals, concepts of open and closed surfaces, and the various important theorems, Stokes divergence and gradient theorems, how to move back and forth from one integral, say 3D to from volume integral to surface integral, or surface integral to line integral, and things like that. And why do we need to do that? Where do we need to do that? And things like that. Then we learned about conservation equations of mass, momentum, and energy, the integral and differential forms of the governing equations. Week 3, we went further into some more involved concepts like inviscid and viscous flows. How do you differentiate them, compare them? What do we mean by potential flow and boundary layer flow? And then how does compressible and incompressible flow compare? Where do they occur? Why do they occur? And then laminar and turbulent flows as well. So we also talked about some of the most important equations like Navier-Stokes equations, Euler equations, Bernoulli's equation, Laplace equation, and so on. And we learned about important concepts like substantial derivative and its connection with fluid element acceleration. We learned about the significance of Reynolds number. We learned about fluid friction due to viscosity, slip and no slip conditions in the context of the governing equations that we apply them to, say, the inviscid versus the viscous equations. And then what happens when you have favorable, adverse, and neutral pressure gradients in viscous flows, consequently attached and separated flows. All these were discussed in week 3. Week 4, we did a more in-depth study about airfoil, its geometry, pressure distribution, important points like the aerodynamic center and center of pressure lying on the airfoil. How do we define those points? The characteristics through the CL alpha, CLCD, CM alpha curves, and then aerodynamic behavior of an airfoil at low and high angles of attack. Therefore, attached and separated flows, stalling, the significance of high lift devices, multi-element airfoils for moderate to high angle of attack operations, even a little bit about trailing edge noise acoustics. So a lot of things related to airfoils was covered in this week. We also discussed about the potential flow theory through the different elementary flows like doublet, point vortex, vortex sheet. lifting and non-lifting flow, Kutta-Joukowski's theorem, Kutta condition, Kelvin circulation theorem. We learned a little bit about what is called as the thin airfoil theory, a very famous theory in the world of airfoils. And we discussed about symmetric and cambered airfoils, how their characteristics are similar or different. A lot was discussed about the airfoil geometry, what we mean by a chord line, camber line, thickness distribution, leading edge, trailing edge, and so on. Week 5, we extended the 2D wing theory or the airfoil theory to finite wing theory, where the wing has a finite span. And then we learned about the Prandtl's lifting line theory, which is a very elegant, simple method of trying to explain the aerodynamic characteristics of a finite wing. Thereby, we brought in the concepts of the horseshoe vortex, bound and trailing vortex, and associated theorems like Helmholtz theorems. We saw how the lift distribution acts over the wingspan, how the aspect ratio, sweep, taper, all these affect the wing's aerodynamic performance. We learned about induced drag factor and its variation with taper ratio. We learned a little bit about delta wings also and their associated vortex roll-up, vortex-induced lift, vortex breakdown at high angles of attack, and so on. Towards the end, we learned about flapping wings, which we see in birds, and man-made flapping devices. When we discussed about the finite wings, the fundamental concepts related to the flow past the wing was discussed in detail, where we discussed about the wingtip vortices. We discussed about the downwash, geometric, and induced angles of attack, and the consequent effective angle of attack, why an induced drag would form on a finite wing, the explanation that was discussed. So all this, along with week 4, had to do a lot with wings. Then in week 6, we moved on to full potential equation. Basically, we were moving into compressible flows, and we started with full potential equation and its application. Then we further discussed about shock, expansion wave theory, supersonic flow past a flat plate, flow through a CD nozzle, transonic and supersonic flow past an airfoil, shock boundary layer interaction, shock tubes, and preliminary concepts of hypersonic flow. So this week basically, in a nutshell, looked at some of the very important concepts associated with compressible flows. That means where pressure variations in the flow can have significant influence on its density variation. That is where we talk about the compressibility effect coming into picture. And we learned quite a bit on compressible flow characteristics in this week. 7th and 8th weeks of the course were spent on discussing about some of the basic computational aspects of aerodynamics. And we started with the idea that we have to choose a mathematical model for solving a given problem, looking at the flow physics. So we have to choose that when we are solving flow past an airfoil, whether we need to use thin airfoil theory or the potential flow models, which are basically solving the Laplace equation, or if it is a compressible case, then it's a velocity potential equation, or do you need to solve Euler equation or Navier-Stokes equation. So you need to be very well aware of the assumptions and approximations that are made in each one of the models. And thereby only you should be able to make a rational choice in terms of the equation that you choose to solve. And then what do you expect to come out as an outcome of such a solution? So those things were discussed in the beginning to develop the appreciation that choice of mathematical models is the first step in any kind of computations that we perform. And then once we are very sure about the mathematical model, we have the governing equations, we start doing the different kinds of approximations which need to be done for doing the computations. So we begin with the panel and vortex lattice methods, which were used in the very early times. Even now they are used in initial phase of the design, and then they are followed by more extensive solutions of the Euler and Navier-Stokes equations. And these 2 weeks basically took us through that kind of an exposure. We also learned some basics of solution of the partial differential equations. First, we learned the classification of PDEs. Excuse me. Followed by the characteristics behavior, the initial and boundary conditions, equilibrium and marching kind of problems, and the different steps, the pre-processing step where you generate the grid and discretize the domain. And then you look at the discretization of the governing equations to make use of suitable numerical schemes based on their stability, accuracy, and so on. And then finally, once you are done with the solution, you post-process the results and try to interpret. Week 9 to 12 were spent on experimental aspects of aerodynamics. So in week 9, we discussed about wind tunnels, different kinds of tunnels. They are the experimental tools. We learned about design basics, the significance of similarity analysis, scaling of internal models, and safety issues. Week 10 dealt with flow visualization techniques, model design and fabrication, positioning system, measurements involving mechanical sensors, and some important sensors like pressure ports, pitot-static tubes, mechanical balances, and so on. Week 11 dealt with measurements involving electronic transducers, electronic pressure gauges, strain gauge-based balances, data acquisition system and software, and measurement uncertainty. And finally, in week 12, we learned a little bit about velocity measurement using particle image velocimetry, which is basically a laser-based technique. And it's a non-intrusive kind of measurement. And then we discussed how wind tunnel and associated instrumentation are used for performing aerodynamic studies. Some examples were discussed. And then we had a very quick discussion about the course contents and doubt clarification and so on. As we head towards the end of the course, I would like to tell you that you should very thoroughly revise the contents of the course. If you are preparing for the end course examination, then you should also practice both numerical problems as well as some small derivations. Make sure that you remember the important equations. Make sure that you remember the important details regarding derivations or regarding some schematic sketches and so on. And if you have solved the assignments very thoroughly, then you should be able to do reasonably well in the final examination. If you are not taking the final examination, even then, please make sure that within the next few days, please self-test yourself to make sure that you have retained a good part of what you have learned in this course. Make your own notes and archive all the contents so that it stays with you for a long time. I think we do not have any further queries or questions coming up, and I therefore would like to close this session 3 of the Fundamentals of Theoretical and Experimental Aerodynamics rerun course. Thank you once again for your very active participation, and I wish you all the very best.